if we're going to take a product, a hard product, where we have actually a product of 3 factors here, right? Go ahead.
1 times 15.
Okay, so you're going to take the first 2? Perfect, good. I've got 3 numbers here. They're complex numbers, but they're just numbers. When I multiply numbers, I always have to multiply in pairs. So you're on track here. So the first suggestion is, let's take, for example, the first 2, boil those out. Okay? So product of the first terms would be 15. What about the product of the outside terms?
Negative 6i.
Inside terms? 195.
Yeah.
And then last? 78.
Negative
Good. Negative 78. Now negative 78. What? I squared. Right. Good.
Wait. Oh, yeah.
Okay. So what's that going to do? Leah?
I squared would make it to a -1 and then you get positive.
Okay. Good. Changes the sign. Right. So the I squared. All that's going to do is make that a positive. Right. Okay. Make sense?
Oh.
Okay. Right. Okay, so then all we have to do from that first product then, once we've distributed, boiled it out, just add up like terms, right? So we'd end up with 15 plus 78, what's that? No calculators. 93. Negative 6i plus 195i.
189.
Good. 189i. And that's the simplified product of the first 2 factors, right?
And you boil the next.
Good. So all we'd have to do then is just repeat that process with what we ended up with times the 3rd factor. Okay? And you're going to get really big numbers when you do that, aren't you? But they're just numbers, and you're going to combine like terms at the end and get some very large values of A and B, but nonetheless, just numbers. Okay? We won't even do it. You could though, right? Same process. You have to do it in pairs though. Okay, what about stepping back to one like this? Really simple, isn't it? What do we do here?
You just subtract, like we would subtract -2 plus 3.
Okay, good. So we're just going to combine like terms, aren't we? One way you might help organize when you're adding up lots of complex numbers at the same time, one way to make this process a little bit easier to follow and a little simpler is just distribute when necessary to get rid of all the parentheses and then just add up like terms. So for example, on this first complex number here, do I need to distribute anything? No, it's just a 1 out front. Distributing 1 doesn't change anything, but I can get rid of the parentheses by doing that, right? We don't really need to do anything. We can just get rid of them. We end up with -2 plus 7i. What about for the second complex number? Do I have to distribute anything there? -1. Yeah, we have to distribute that -1, which gives us what 2 terms? Plus 3. Good. And then the last one, yeah, just nothing, right? It just stays the same. All we have to do is add up like terms. So for example, if we're going to add up the real numbers here, no i's, let's just add those up as we go. -2 plus 3 is 1 plus 21. Okay. What about the I terms? 7i plus 8i is 15i minus 13i. That's my answer. Right? Okay, no big deal. Okay, what about division? Yikes. What do we do with division? Somebody different here. Division. What do you think? Adam, do you have an idea? Remember what we do with division? No? Okay. Somebody different here. Say it again. Okay, now we're on to something. Okay, when we divide complex numbers, the way we simplify is we multiply top and bottom by, okay, not quite the bottom, almost the bottom, but the conjugate of the bottom. Good. So we'll multiply both the top and the bottom in this case. Whoops. That's kind of fun. Times the complex number. Instead of 9 plus 6i, it would be 9 minus 6i. conjugate. Okay? And let's see what happens when we do that. If we FOIL that out on the top, product of the first terms would be negative 90. Product of the outside terms, plus 60i. Product of the inside terms, negative 63i. And product of the last terms, okay, so it's gonna be plus 42, whoops, I squared. Good, exactly. But the I squared is gonna change that to a minus, right? Okay, make sense? What about the bottom?
Negative 42.
So it's negative 42, yeah.
Oh.
Okay. So what about the bottom? Now, on the bottom, when we FOIL out the bottom, they're conjugates. So product of the first terms would be 81. What's going to happen to the product of the outer terms plus the inner terms? Anybody know? They're going to cancel. Guaranteed, they're going to cancel. So you don't even have to do them. We could just skip right over to the product of the first terms plus the product of the last terms. What's the product of the last terms going to be? Okay, when you're multiplying conjugates, you're always going to get a positive times a negative, right? Which is going to be a negative, in this case 36 I squared, but you're also always going to get an I squared there, right?
So it's gonna be 36.
Right, right? And so it always ends up being a plus b squared. It always ends up being a squared plus b squared every time when you multiply complex conjugates. Now, just to so you can see that the middle terms do indeed cancel, if I do the O and the I, outer product is going to be minus 63i, nope, minus 54i, whoops. Minus 54i, inner product is plus 54i, so those both cancel, as advertised, right? And so we end up then with, on the bottom, 81 plus 36 is just 117, right? Real number, we got rid of the i's, that was the whole point. On the top, when we add up like terms, negative 90 minus 42, negative 132, good. And then 60i minus 63i, okay? And if we want to write this in standard form, we have to write it in the form a plus bi, so we have to separate this, don't we, into two different fractions. What do we end up with? Good, negative 132, 117, so that's a, minus 3 1/17 times I, so that's b, right? Make sense? Yes, sir.
What do you do if there's a square root in like the original equation?
Okay, if there's a square root in the original one, you do the same thing. Only instead of multiplying, it makes it a little tougher because instead of multiplying by like 9 minus 6i, it might have been square root of 3 plus square root of 7i or something, right? And so you're gonna get harder answers only because you have to multiply, when you FOIL it out, you have to multiply those square roots. Probably you're not going to be able to, like here we were able to combine these terms real nicely. Negative 90 minus 42 gave us negative 132. Probably not going to happen if we have square roots in there. I'm going to get some kind of square root plus some different kind of square root, and they're probably not going to combine. So I get a big, long, ugly looking answer. Okay, that one I'll make a bonus. I want you to do it if you can, but I won't mark you down if you don't get the right answer on that. Okay? All right, so what would I do with this one? What's one suggestion? What's one way to do this? Cody, what's one strategy for this? What do you think? Get a single answer out of this.
I don't know.
Tony, you have an idea? Oh, wow, there's a good idea. Okay, I was expecting people to say, first of all, and this would work, we could just divide the first complex numbers the same way we just did, right? get an answer, divide the second two, get an answer, and then add them up, right? Okay, now what's the hardest thing to do out of all the stuff we've looked at? Addition, subtraction, multiplication, or division of complex numbers? Definitely division, isn't it? Okay, that's probably not one you're looking forward to doing because you'd have to divide how many times if you do it that way?
Multiple times.
Twice, right? Once for this quotient and once for that quotient, and then add up like terms. 2 divisions, that's a lot, right? But what Tony said, she had a really good idea. She saw that we had a common denominator there, right? And so as long as you have a common denominator, you can easily add fractions. Isn't that what you're gonna say, right? So we see that we have a -4 minus 5i in both fractions. So why not write this as, on the bottom, we have the common denominator, -4 minus 5i. On the top, we just add like terms. We're just adding those up, right? Like we would with a normal fraction. If I had something like 2/7 plus 3/7, how many sevenths do I have? 5, right? Same kind of thing here. I could just combine, just add up the complex numbers on the top and get what? Yeah, good, minus I. And now, how many times do I have to divide? Once, much better, right? Good idea, right? Okay, questions? Would have worked the other way, just more work to do. Okay, so I want to skip that for now. Let's take a look at a couple. What about one like this? Yikes. What is it? No, that's not going to work on the test. Okay.
Wait,
Well,
you go back to mine.
I mean,
sure. Yeah. That's all right. Okay, and I will have this up on the playlist by 3:30 today, I promise you. It's easy to do. I'll just upload it, it'll be on, it'll be there. Okay?
Thank you.
You betcha. Okay, so what about now? What about one like this? These are very simple, honestly, very simple. There are 2 assignments on complex numbers. The first one is the harder of the 2. The second one has a couple questions at the beginning that are sort of like that last one we looked at was actually at the beginning of the second assignment. But most of the second assignment deals with the complex plane, and they're really simple problems to do. Okay, so what about this? Now, if we're trying to, we've got this, let me make this a little bigger so you can see it better. Okay, so our goal here is we want to figure out which of those vectors represents the complex number -8 plus 5i. Tony, what do you think? Or not Tony, Leah, what do you think?
It's error because you look at the real axis and that's -8. That's the real number, and then you look at 5i, which is the imaginary axis, so it'll begin.
Good, okay. So this is written in standard form, a plus bi, isn't it? Right? And so really all we're trying to do is we want to find out what's the value of a, which is -8. And that's going to be the horizontal component or coordinate of the ordered pair. What's the value of b? Just 5, not 5i, it's just 5, isn't it?
Why?
Because b is just the number that's being multiplied by I. Okay? So then that means that it's represented in the complex plane by the ordered pair -8, 5. So we would just go back 8 and up 5, which puts us right there.
That's it.
Okay, that's it. And so, what's that? Make them all like that? No. Okay, so that's an easy one, isn't it? There are some other questions, though, on that assignment that are sort of like this. They want you to do, not to identify the complex number, but to find the value of the modulus. Okay, so it's the value of the complex. It's kind of like an absolute value. And remember, this is important because a lot of the times, I gave you an example of something that we do with complex numbers a lot, and that is we use complex numbers to calculate complex impedances in complicated circuits, right? So if you have lots of circuit components nested together on the same chip, and they're all contributing to the overall impedance of the circuit, it's really difficult to add all those up using real numbers. It's much, much easier to use complex numbers instead. But when you're done, you get an answer like this. Now, impedance is really just a fancy word for resistance. If you take physics, I'm sure you'll mess around with one of these. You might even, if you're doing some wiring at your house, you might even use one of these. A multimeter. A multimeter is they're cool little devices. They just have, you plug little wires in with little pins on the end. And when you touch those to something, you can measure the electrical properties between those two leads, those two little pins that you're touching something with. If you want to measure impedance, you're measuring resistance. So you would just turn the setting to resistance, and if I put the two of them down, if I put them on opposite sides of a person's hand, you could measure the electrical resistance, kind of interesting, in a person's hand from here to here. How much resistance is there to electricity flowing through your body from here to here? Your hand is it's a resistor. I mean, it's a resistor, but it does conduct electricity a little bit. And so you'd get a certain number. You get back something like, I don't know, 23 ohms, let's say, something like that. And so that's going to give you, that's just like you'd measure length in meters, you measure resistance in ohms. If you if you put them both down on a metal cookie sheet, you'd get a really low resistance because it's metal, it conducts. If you put them on opposite sides of a styrofoam cup, you'd get a really high reading because it's very little electricity is conducted through styrofoam cup. It's an insulator, so you'd get an answer that would be hundreds of thousands of ohms. But we have to somehow, yes. Say it again. Rubber would be a really good insulator, and so rubber would give you a really high resistance, which is why rubber would be, if you ever had to pick up something that might be like a live wire, if you had a real thick rubber glove on, you'd probably be okay. I mean, I'm not recommending you do it, but you get my point. Okay, so anyway, good question. Okay, but so how would you then, I mean, if you get some answer back from when you're calculating this complex impedance that says -8 plus 5i, well, what's that? There isn't an option on your multimeter that gives you complex numbers with i's in them. They'll never show up on there. They're all real numbers. What we need to do is we need to find out how big is that complex number, because the size of that complex number is going to tell us the amount of resistance, right? And so that's what a modulus really means. A modulus, one way to think about a modulus, that's kind of a cool way to think about it, is it's just the distance from the origin in the complex plane. If you think of it that way, every complex number just amounts to a distance, and if the number is all imaginary, it's really simple. Like, for example, if we had the complex number, let's say we had the complex number -3i, right? So, graphed in purple. What's the length of that vector? The length would be 3, right? Distance is always positive. Distance is, right, does that make sense? So it would just be the absolute value of -3, which would be 3. Make sense? Easy. What if it were, we'll do an orange one, what if it were -7? So it was right there. It'd be 7, wouldn't it? And in that case, the modulus really is just an absolute value. When you're talking about only real numbers, modulus actually becomes the absolute value, right? See my point? But when there's a real part and an imaginary part, it gets a little harder to find that distance. It's not something you can just count, it's something you have to calculate, right? And so how would we do that? Well, we could just turn this into a right triangle, right? And wouldn't the length of that vector, meaning the size of the the size of the complex number, isn't it always just going to be the hypotenuse of the right triangle we create?
Yes.
What are the lengths of the legs in this case? Okay, so the lengths would be, I could call it -8, I could even just call it 8, right? If it's a length of a leg, it would be a positive number, so 8 and 5. And how would I calculate in a right triangle the length of the hypotenuse? A squared plus B squared equals C squared. If A and B are the legs and C is the hypotenuse, right? So we'd end up with the magnitude of this thing, call it that, right? Z usually is what the variable we use for a complex number. And so the absolute value bars mean modulus. So the modulus squared would equal 8 squared plus 5 squared, what would I have to do to solve for the modulus then? Can I just square root it, right? So my answer would just be the square root of 8 squared plus 5 squared, right? Make sense? Now we can make a formula out of that. It's really simple. Instead of pinning it down to be 5 and 8, what if we just called it A and B, right? If we just know that A is the real part, B is the imaginary part, don't we always end up with something like this? Then don't we always end up with something like this? The modulus of A plus B times I would just be the square root of A squared plus B squared every time. Easy, right? Okay. So what would be the modulus of -2 minus 3i? Square root of -2 squared, but what do we don't square negatives, what do we do instead? Square positives, so 2 squared plus 3 squared, so square root of 4 plus 9 squared is 13, right? And that's just a number. If I put that in my calculator, I'm just going to get back something like, 3 point something. And that would be if it were talking about resistance, that'd be how many ohms? Make sense? Okay? Easy. Last one. What about this? Okay, we're getting to the point now where we're starting to be able to solve harder quadratic equations. What do you think, Jake?
You add the 11 that's not on the fraction to the -6.
Okay, good.
And then you multiply by -5.
Okay.
And then square root
Okay.
the
How are you getting these steps? How do you know which order to do those steps in? Yeah, this is reverse of order of operations, isn't it, right? And by now, you probably don't even think of it that way. So what do we call it, SADMAP? SADMAP? Okay. It's SADMAP. Okay, and now the other question I have then is, why does that work? Why did Jade know to do that in this case? She's awesome, true. But why else? What's the 1x? Exactly. Good. Okay, there's 1x there, so I can always isolate it by doing SADMAP, right? So let's quickly zip through that, and then that'll be it. Then you guys can have the rest of the day, and you have tomorrow to kind of wrap up the assignments. So first step, we already told us, Jay told us, first one is we're going to add 11 to both sides. That's the add or subtract step. That's going to leave us with, on the left side, -15x plus 10 quantity squared over -25 equals what? 5? Right? Agreed? Okay, next step, to try to get our quest to get the x isolated on the left side, I have to undo dividing by -25, which means I multiply by -25, right? So if we do that,
Oh, yeah.
so those cancel, that's good, right? That's our multiply step, and we end up with, if we do that, that just gives us the quantity -15x plus 10 squared equals what? -125. Okay, next we were supposed to deal with exponents, so that means square rooting in this case, right? Square rooting both sides. Right? Okay, that undoes the squared on the left, which is nice. That leaves us with a -15x plus 10. What about the other side? Ah, we got a negative number under the square root. What does that mean? Uh-oh. I. Right, that means an I, doesn't it? Okay, that's where that imaginary unit comes in. So we end up with equals, that square root becomes the square root of 125, positive 125 times outside of the radical and I. What am I forgetting though? Plus or minus, good. Okay, we can go a little further with that. Can I simplify the square root of 125? No.
Why does the I go on the
15's
outside?
225, 15's 25. But is there a perfect square that divides into 125? 25, right? I can break that up into the square root of 25 times the square root of 5 times I plus or minus, right? So we end up then with, finally, the square root of 25 is 5. So plus or minus 5 times the square root of 5 times I. On this side, now what? What do you think? Okay, good. We're going to subtract 10 or add negative 10, same thing. And so that goes in front of the plus or minus. And we get negative 15x equals negative 10 plus or minus 5 times the square root of 5i. Last step. Oh, that's not a negative 15, is it? I don't know why I wrote down negative 15. It was never supposed to be a negative 15. That was my mistake. Right? That was just a positive 15. So let's change all those. It could have been, but it wasn't.
We did it wrong?
No, we did it right. I just wrote down the wrong stuff every time.
We did it wrong.
So I guess we did it wrong. So now if we divide by 15,
Oh, yeah.
the 15s cancel, and we got our answer, right? Almost. Okay, one last step here.
Wait, isn't it just 5 I? Not 15. Square root of 15.
Oh, it is 5. You're right. Messed up again. Hang on. Good thing you're watching me like a hawk here, right? Okay, now. Okay.
Why did 15 and 15 cancel?
Say it again.
Why did 15 divided by 15?
Where do you see that?
The second one from the bottom.
Right there?
Is that
Oh, those
right?
did. Right, I divided both by 15. Remember, I divided top and bottom by 15 to get rid of the, right?
Okay.
Or divided both sides by 15, I should
So
say.
it left.
Right. Okay, so this is what we're left with, right? Okay, but I've got to write this in standard form. A plus or minus BI. So what does that mean? Okay, so I'm going to split it up into separate fractions. I get negative 10 15ths plus or minus 5 square root of 5 over 15 times I, right? Okay, but if I put that in there, it's going to say almost, but it's not simplified. What's wrong? No? Ah, fractions can be reduced, can't they? Okay, last issue then. This fraction, negative 10 15ths reduces to, good, negative 2/3. What about this one over here? Okay,
1/3.
yes, good, okay. So the 5 over 15 part reduces. Now that's the same thing. Reducing a fraction is the same thing as dividing the top and bottom by the same number, isn't it? So in this case, I could divide both the top and the bottom by 5. If I divide the top by 5, what do I get? What's 5 times the square root of 5 over 5?
Square root of 5.
Yeah, I'm just left with a square root of 5, aren't I?
So it's
On the bottom, 15 divided by 5 is, so there are my two answers,
wait. Oh, never mind.
okay? Right, and in Moodle, I'd have to just enter those separately with a comma in between. One with the plus sign, one with the minus sign, right? Got it, good. 205.